would like to be there because of the many social events and some sessions in between, but they are they seem to be less important than those social events that you are mentioning. No, I'm just joking. The sessions are exciting, and I am happy to introduce the first paper. Can you confirm that you, Federico and Stefania, are going to allow the screen sharing? Should I do anything?
Yes, we are going to do.
Okay, thank you. So I will leave the floor to Stefano, I suppose, for presenting the paper by Stefano Bistarelli, Maria Chiara Meo, and Carlo Taticchi, Timed Concurrent Language for Argumentation.
Viviana,
thank you.
Carlo will give the talk.
Okay. Well, I did not check before. Sorry, Carlo, the floor is yours.
Well, thank you. I'll try to share my screen now. Is it working?
Yes, it does.
I cannot see
okay,
anything.
Carlo,
sorry.
I suppose you have around 20 minutes,
Okay.
20-25, and then some time for questions.
Okay, fine, thank you. So let me start with this presentation about a work we did on timed concurrent language for argumentation. So argumentation is a set of disciplines within the AI field, and it deals with information. In particular, it deals with representing information and provides tools and formalism to reason with knowledge and to draw conclusion from it. You can imagine a debate between two people or two political opponents, for instance. And these counterparts need to present arguments that needs to convince the audience, need to be accepted by the audience, and at the same time need to defeat whatever is the point of the arguments coming from the other counterparts. And in this kind of application, this kind of examples, you can already see that the information we're talking about is not static, but it somehow changes over time, and so it kind of evolves. It's not the same from the beginning to the end of the dialogue, but it changes. And these changes of information, this notion of time, we want to consider in this work. To give you a brief overview, I'll start with some background on argumentation frameworks, that is the building block of argumentation theory. And I'll talk about acceptable arguments, and then I'll present an extended version of these argumentation frameworks which introduce time. And then I'll proceed with our contribution, that is this time concurrent language for argumentation. I'll show you both the syntax and the operational semantics. And I'll also show you an example of application in which we are able to model timed argumentation frameworks. So, as you can see from this example here, an argumentation framework can be represented through a directed graph. Arguments are the nodes of this graph, and the edges represent attack relation. So the arguments are abstract in the formalism we use, and they stand for placeholders of the information underneath. The attacks represent an attack between the two arguments. Whatever A is saying, it is attacking the argument B. And so the goal with these frameworks is to identify subset of arguments that argue together, that can be accepted together. The basic requirements is those of conflict freeness. That is, you're looking for subset of arguments that do not attack each other. An example, you can see all the conflict-free subset here. An example is provided by the arguments A and C. There is no attack between A and C or vice versa, so A and C argue together according to this conflict freeness criteria. I can be more restrictive and select different kind of acceptable subset of arguments. I can use different criteria that we call semantics. For instance, according to the admissible semantics, we restrict only to those sets in which arguments are able to defend themselves against the attack of the other arguments. We show an example here with the argument C that is attacked by D, but then C attacks D back. And so we say that C is defended, and indeed the singleton C is an admissible extension, that is an admissible subset of arguments. There are several of these semantics. I just listed 3 here, the last one being the complete, that is even more restricted than the admissible one. There are more. We just need for now to know that you can select this subset of arguments. And these are called extension-based semantics, because what you obtain at the end is a subset of arguments, and those arguments are accepted, while the arguments outside the extension are rejected. There are another 2 notions we can give about acceptability. And we say that if an argument is accepted in at least one of the extension, with respect to given semantics, then the argument is credulously accepted. On the other hand, if an argument is accepted by all the extension of a given semantics, then the argument is skeptically accepted. Now, we've seen extension-based semantics. There is another approach we can use to identify good arguments or elements, and this is the restatement leveling. It consists of a set of rules which allows you to label the arguments with 3 statuses. We say that an argument is in, we highlight that in green, if it is attacked only by out arguments. In arguments are those that are acceptable and correspond to the extension identified by the extension-based semantics. Then we say that an argument is out, B and D in this example are out arguments, whenever it is attacked by at least another in argument. And in the other case, we say that the argument is undecided. We don't know how to label this argument between in and out, so we say that it is undecided. Okay, now we were talking about time. One of the methods of the approaches you can use to introduce time into this kind of frameworks is by using timed argumentation frameworks. In this approach, you see that arguments are endowed with an availability function, which specify the intervals of time in which each of these arguments are available. And for example, in this framework here, we begin with the only argument E being available in the framework. You can see it here from this timeline. After 10 units of time, we can say seconds, also argument A is available from this framework. And after 10 more units of time, C becomes available, and at t equals to 30, also B appears. And at any time in this framework, you can compute the sets of acceptable arguments. You can also label them according to the labeling function we've seen before. And yeah, so you have this transition of arguments that enter and exit the knowledge base. And we wanted to consider the notion of time actually to integrate in a language that is able to model interaction that took place between intelligent agents. These agents use argumentation frameworks as the shared memory to communicate. And this is not because it enables the use of the tools provided by the argumentation theory, like the various semantics, in order to reason about the acceptability of the information that these arguments share, that these agents share. For this language, we use bounded asynchrony for the computation. That means that computing requires a bounded amount of time, it's not instantaneous. And we use maximal parallelism, that is, all the available actions are executed simultaneously by the processor. This is in contraposition with the interleaving approach, in which just one process can be handled at a time by the processor. And you can see here that our language has a set of actions, we denote with A. We have terminals such as success and failure. We can add or remove information from the knowledge base. And an action can also be an expression or a procedure call. We will see an example of this procedure call later. And let me just show you the operational semantics in order to also better describe the construct of the language. So the add and remove operation do what you expect. You can add or remove part of the underlying argumentation framework. You specify a set of argument, a set of attack relation. You can either add them or remove them from the knowledge base. Then we have a syntactical check. You can check whether a set of arguments and attack relation belong to the shared memory, that is to the argumentation framework. And we have to specify a time t, that is a timeout for this check operation. And so it works like this. It tries to verify if the set of arguments and attacks are in the shared memory. If they're not in the memory and the timeout is greater than 0, then the timeout is decreased and the check is performed again in the subsequent step. If the timeout reaches 0, then the operation fails. We also have semantical tests. We have two kinds of tests, one credulous, one skeptical, that they are according to two notions of skeptical and credulous acceptability we've seen before. They work like the syntactical check. The difference is that the check is just on the syntax, on the information that you find on the knowledge base. The test looks for the semantics, that is, whether the argument, the information in the shared memory is acceptable or not. And indeed, you can ask, given an argument, a label between in, out, or undec, as we've seen through the 3 colors, the labeling example, with respect to a semantic sigma. And you can ask whether the argument A has this specified label. And also here you have the timeout as before. When the timeout expires, the test fails. Then we can compose operation through the parallel composition. This is the classical one. We also have an operation for a guarded parallelism. We called it guarded, and it is able to, it allows you to execute all the expression that can be executed. That is, if you have two expressions that can be successfully executed, both of them can continue and can be executed. And the guarded parallelism only fails if all the expressions specified fails. Then we have the non-determinism, that is the classical one, and we also introduced a sort of prioritized non-determinism that realizes an if-then-else construct. We have two expressions. We first try to execute the first one. If the guard of the first expression is satisfied, so the expression succeeds, the execution continues with whatever comes after the expression, an action or another expression. If the guard of the expression cannot be satisfied, and in particular when the timeout associated to that expression expires, then we try to execute the second expression. So if the first one can be executed, we go with the first one, otherwise else we go with the second expression. And okay. Now, by using this construct we have seen, we can, for example, model timed argumentation frameworks. This is just an example. of what we can do with this timed concurrent language. And for this example, we use a particular procedure we call sleep. It is realized starting from the syntax of our language. And in this case, we only require one parameter, that is an amount of time t. So the sleep construct simply makes an agent wait for t instant of time. Technically, it performs a dummy check for exactly t times. And this check always succeeds. And due to the bounded asynchrony hypothesis, it requires 1 unit of time to be executed. And so after t checks, we have waited t units of time. And we need this sleep to simplify writing this program here. For this example, we consider that each agent handles just one argument, but you could also have just one agent taking care of all the arguments in the framework. In this simple example, we just took care of 2 arguments, A and B. Both are not available at the beginning of the when the time starts, but we see that A is available after 10 units of time, B is available after 30 units of time. So what we do to emulate this availability function here is to make agent A sleep for 9 seconds, and then we perform an add operation. This takes one further unit of time. And so at t equal to 10, when A is available, A is also added to the knowledge base. Then A keeps being available for 30 units of time. And in this period of time, the agent A just sleeps. And so A is still available. Then we remove A because it's not available anymore. Then we re-added it, and so far and so on. And for agent B, the idea is the same. We make it sleep. Then we perform add and remove operation to emulate the function of this availability of the arguments. We compose everything with parallel composition to obtain the same exact kind of interaction of the arguments as in the timed argumentation frameworks. We also have a web interface. I'll show you a very quick demonstration. You can either write a program by hand, or you can select one of the proposed example. You can run the program, and you can see the final state of the shared memory, that is, which are the arguments in the underlying argumentation frameworks. And we also see here represented the corresponding timed framework. We can also choose to run the program step by step. And in this case, you can see the evolution of the memory and of the timed argumentation framework while each step is executed. Okay, so back to the slides. I'm about to conclude. I show you this concurrent language for argumentation that includes the notion of time. Okay. And I showed you an example in which we use the construct of our language to model timed argumentation frameworks. And in particular, you can see that the set of arguments that are in the store at a given t coincides with the set of arguments that are available in the timed argumentation framework at time t. And as consequence of this, we have that also the set of arguments that are acceptable in the store at time t coincides with the set of arguments that are acceptable in the original timed argumentation framework at time t, of course, with respect to a given semantics. I'll show you an implementation that is available online. And actually, our language can do more than just modeling this timed framework. In the example, we just used a few of the operations of the language, and in particular, we didn't use operation that takes into account the semantics of the arguments, that are the test operations. Well, we can use them to implement more complex interaction between agents, such as the negotiation, the debating, or the persuasion, in which you need to be aware of the semantic status of the arguments. That is, you need to know whether they are accepted or rejected. And we use maximal parallelism. We also would like to investigate the interleaving approach, which is kind of more natural for application like debates or negotiation. We also would like to study the acceptability notion when considering time, so that we ask questions like, are two arguments A and B acceptable together in a given time interval, for instance? And then, since we can modify the status of acceptability of the arguments in our knowledge base, we have connections with the believer revision and the AGM frameworks. We would like to investigate further on this direction. And this concludes my presentation. Thank you for your attention. And if you have questions.
Thank you very much, Carlo, also for your nice and clear introduction to the argumentation framework in general. Okay, I think I cannot see the chat. So if questions are posted on the chat, I cannot manage them because I cannot see it. So I suggest that people, okay, for example, Alberto raised his hand, and Alberto, please just turn your microphone on and speak. Thanks.
Can you hear me?
Yes.
Yep.
Okay, yes. So my question is about the interaction between the algorithm for deducing attack and the evolution of the knowledge base. If it takes too much time to deduce whether an agent is attacked or not, or an argument is attacked or not, then the knowledge base may change. In the meantime, I make some deduction. So can you provide an interaction between the two time systems? The meta, the reasoning time and the database changes.
Okay, thank you for the question. So we actually didn't take into account this difference in timing between detecting the modification and performing the operation of our language. But yeah, for sure, it should be considered in practical application. And yeah, one thing that we can do in our framework is to make the agent wait. If I can find the slide, yeah. For instance, we can make the agent wait. So in a certain we have the possibility to wait until the modification can be detected. But yeah, I mean, we didn't consider this yet, so it's definitely something to look into. Thank you.
Thanks.
Alberto, if I can add something.
Yes, please.
Before coming to this implementation, that is maximal parallelism between the agents, we indeed created and implemented using real thread on operating system. In this case, we had a time real time passing. So this probably is connected to your idea that we have to take in account the time. And also in other things, indeed, checking the semantics, the operation, the semantic operation could be expensive. However, there are some semantic that can be polynomially checked, and the idea is to use this polynomially checked semantics, like the grounded one, the specific, a special one with respect to the complete one that Carlo described. Thanks, Alberto.
It would
Thank
be
you, Stefano.
Yes, thank you, Stefano. Yes, it would be nice to have a formal system where this meta time, so to speak, is explicitly entering as a variable in your deduction system. But
Okay.
Just a comment. Okay, good.
Yes,
Thank you very much.
We can try to take care of this. Good question. Thanks, Alberto.
You're welcome. Yes.
Laura, I can see your hand raised.
I would like to ask, your framework is very general. And my question is, you have at some point, you have said that each agent may handle one argument. And I would like to ask whether it is also, you also consider the case in your framework where an agent deals with more arguments, and maybe the arguments of each agent are, so they share some argument, they see only some part of the graph of argumentation graph. This is orthogonal, of course, to the temporal issues.
Thank you. We in the example we showed, we had an agent for each argument. And this is just a choice. You can have one agent taking care of more than one argument. You just need to take care of the time. That is, you need to make the agent sleep, for example, between adding two arguments. If these two arguments are available in different times, for instance, for this example, I could have agent A to sleep 9 seconds, add the argument A, then sleeps 19 seconds, and then add the argument B. Then sleep and remove A, then sleep again and remove B. So A and B could have been easily been managed by a single agent A. You just need to think differently how you want to compose your agents, and you definitely can use less agents to take care of the arguments.
Thank you very much for your answer.
This answered the question.
Thank you. Actually, I had a similar question with respect to Laura's question, so you already answered also my question. I suppose that we might go on unless there is any very quick question. If not, I would thank again the speaker. Thank you. And all the authors, of course. Thanks. And I would move on with the next paper by Giuseppe Pisano, Roberta Calegari, Andrea Omicini, and Giovanni Sartor, a mechanism for reasoning over defeasible preferences in arg2p. And Giuseppe is giving the talk.
Hi, everyone. Good afternoon. I'm trying to share my screen now. Okay, can you see it?
Yes.
Okay, perfect. Okay, I'm here to present you the work, a mechanism for reasoning over defeasible preferences in arg2p. This is, you already mentioned the authors, all the authors. So I just keep the presentation. So let's start for a motivation for this work, a bit of context. We are dealing with conditional preferences, but what are conditional preferences? Normally, in the context of structured argumentation, we have a knowledge base, a set of rules. We want to be able to express priority over these rules in order to obtain priorities over argument in inferred arguments. Normally, in the standard argumentation frameworks that have been proposed, these preferences are strict. They cannot be changed, but are given from the beginning. Now we want to focus on conditional preferences, so preferences on which we could argue about. if we think about it, there are many real-life scenarios that assume our ability to argue over preferences. In fact, we often express preferences depending on the situation we are in. For example, let's take that we have to choose the mode of transport. We have to choose between go by foot or take a bus. Probably we don't have a preference, normally a preferences or our on which to choose, but maybe the weather or if we are tired or other things belonging to our context may influence our decision, and we could form a preference. So a tool, a general purpose tool that wants to be effective in real world reasoning, in a real world scenario, needs to have this feature, needs to deal with conditional preferences. However, an efficient implementation of a model for dealing with defeasible preferences is still missing. So in this work, we try to obtain such a tool, such a mechanism. Our highest requisite is to obtain the highest degree of compatibility with the standard approach for standard structural argumentation. We didn't want to build something too custom, but we wanted to build something that can be just injected in a standard argumentation framework in order to enhance it without particular mechanism. So we propose an efficient implementation for defeasible preferences in R2P. The work is based on Doom's model for conditional priorities. It is a work from 2019. And we provide first an optimized implementation of the base model, and then try to generalize the algorithm, propose a generalization of the algorithm in order to handle arbitrary preferences relations over arguments. But let's take a step back. Now I'll give you very few notions in the context of structured argumentation. So in structured argumentation, we encode the knowledge through defeasible rules that are simply the rules that can be defeated by contrary evidences. A set of defeasible rules form a defeasible theory, and we can build arguments chaining the rules belonging to the theory. Then, based on the internal structure of the arguments, or on their form, we can have an argument that can attack another argument. We can derive attacks between them. So using attacks and arguments, we can build argumentation frameworks. We have an example of an argumentation graph where the nodes are the arguments and the edges are the attacks between the arguments. And through semantics, we can compute the admissibility of these arguments. We leverage on three-value labellings, so arguments can be accepted, rejected, or undecided. In order to deal with defeasible preferences, Dunst introduces two more notions: preference arguments, that are arguments that can have a preference over rules as their conclusions, and preference-based argumentation graph frameworks, PAF in brief. PAF are a transformation of standard argumentation graph, also accounting for preference arguments. The base mechanism is very simple. The attacks all the attacks are transformed into arguments. We call them attack arguments. And then those attacks can be attacked by the preference arguments if they claim a contrary preference, a preference contrary to that attack. So at the end, we have a different argumentation frameworks containing the original arguments, the attacks transformed in arguments, and the attacks will be reconstructed completely based on the new informations. We have an example of the transformation. We have three arguments. A attacks B and the derived argument B1, and in the respective path, we have that the attack has been transformed in the attack argument at, and now the attack is issued by this new argument. The most important property of this of the path of the preference-based argumentation frameworks is that they are conservative. They are a conservative generalization of standard argumentation frameworks. So we can apply standard semantic or the standard semantics to these new argumentation frameworks to compute the result, to compute admissibilities. And this is very important for a requirement to have the highest degree of compatibility with the available formalism. Another important aspect on which the original work is focused is on the attack relation. As highly simplifying, an attack is not valid if exists a single preference against it. And from that notion comes the main shortcomings of the original model that will try to overcome in the generalization, that the attacks comes from single preference arguments and cannot come from groups of preferences. But let's continue with the implementation. We implemented it in Arc2 Prologue. Arc2 Prologue is a lightweight implementation for structured argumentation. It has been built with focusing on the main notion of interoperability, portability, modularity, and customization, in order to be suitable for highly distributed environments, to adapt to different and most disparate application domains and scenarios. To support these properties, we tried to optimize the transformation, the algorithm used to build a path from argumentation frameworks. And we did it by filtering all the attacks to be transformed, because transforming the attacks into arguments increases the complexity, increases the computational resources needed to compute admissibilities. The bigger is the graph, harder will be to compute the solution. So we try to keep it small, filtering the attacks that have not to be transformed. We transform only the attacks that are impacted by a preference argument in the original theory. In this way, we avoid computational overhead. This is the pseudocode of the algorithm used for the transformation. It is very simple. It is composed of 4 steps. First, we filter those attacks that are not impacted by preference arguments. Then convert those attacks, build a new set of attacks coming from the preference arguments, and then we have the final argumentation framework to be used. This is an example that it has been done using Arc2 Prologue. We have 6 defeasible rules. Most important are Arc0, Arc3 that concludes the conflicting, made a conflicting statement. There are A and not A that are conflicting. And then we have 3 preferences. There are 3 rules claiming a preference. To try to decide between the admissibility on A or not A. Normally, if in a standard argumentation framework, underground semantic, this we would obtain an undecided result. but we can see that thanks to the path transformation that is below on the right, we have that we have three arguments, A5, A6, and A7, that are attacks that have been transformed into argument. And then they can be attacked by the preferences. At final, we can decide for the argument A1 standing for the not A conclusion, according to the preferences that have been included in the theory. But should we be satisfied with this result? The algorithm is sound. We are capable of dealing with the feasible preferences, but what about the use of combined preferences? For example, Aspect Plus frameworks, the Aspect Plus framework, that is the standard, also the standard for structured argumentation, between the orderings that it gives for arguments, deals also with the multiple preferences orderings, for example, the weakest democratic principle. So we need to generalize the mechanism to handle path. This is exactly what we did. We introduced two main notions: the group preference set, the joint preference argument. The group preference set is the set or the possible subset of the preference arguments. In simple terms, it is the set of the possible combinations of the preference arguments that can be built from the knowledge base. Then, for every member of this set, we can build an artificial argument that we call joint preference argument, and add to the argument in the list. In this way, now the attacks will not come anymore from a single preference, but they will come from these joint preference arguments, representing also combinations of single preferences. This is the only difference from the original algorithm. We can see here that it's exactly the same as the one I showed earlier, but the only difference is in the first step and in the third, where we now leverage on joint preferences arguments and no more on preference arguments.
Excuse me, I still see slide 13. I suppose it's my fault.
13?
But yes, it seems you are in another slide. Maybe it's my fault, so...
But I can see the right slide.
Okay, okay. Just to know if...
yes. Thank you.
Okay, sorry. And you have more or less 10 minutes, so I suppose you have enough time. Thanks.
Thanks. I'm almost finished. This is a graphical representation of the transformation from a preference-based argumentation framework, a generic preference-based argumentation framework. Here we can see that the preference argument P, that at first was attacking the attack argument, now is substituted by the artificial argument, the joint preference argument AP. In this case, the combinations of one single preference argument is just the argument AP, and now the attack is issued by this argument. This is an example of the application of this new generic preference argumentation framework. We have also in this case two conflicting rules stating one B and the other one not B. And we have two preferences. One stating the superiority, the priority of R2 on R1, and the other one stating the priority of R2 on R0. These two priorities, preferences combined, should provide the highest should provide that using these two preferences, we should obtain that the argument concluded not be according to the Weikes-Lin democratic ordering is preferred to the one concluded B. We can see here the argument list that has been inferred from the knowledge base. Argument A6 is the joint preference argument, merged preferences. We have one attack argument, A4, and now we can see that how effectively we have that A1, the argument standing for not B, is accepted, or always undergrounded semantic, while the attack argument A4 is rejected, allowing not B to be accepted. The work it is still an ongoing work. It is not concluded because we need to deepen the more computational aspect, like an analysis of the complexity of these algorithms on termination. We started an informal analysis on these themes, and we found that as for the complexity, it should be polynomial. It should be proportional to the number of input attacks and the number of preference argument, but we still miss a formal analysis. As for the determination, we believe that the transformation should always provide a graph, a transformed graph. The problem, of course, in the soundness of this graph in relation with the admissibility computation of the arguments. We need also to provide a formal foundation for the generalization of the preference-based argumentation frameworks that at the moment has been studied more from a computational point of view and not from a formal point of view, so we will continue the work. I've concluded. Thanks for listening. I'm open for questions.
Thank you. And sorry if I interrupted you, but I have some refresh issues with my screen. So maybe there is some question from people in presence. Just in case, I would ask Federico, Stefania to let me know. Otherwise,
no questions from Paolo.
Okay, okay. Is anyone online having some question? Because I have, and my question is a difficult one, maybe not just for Giuseppe only, but for all the authors of this paper and the previous one. I was wondering whether you could see some possibility to integrate time in your framework, if it makes sense given your assumptions, and if it could be feasible from a technical point of view, from an implementation point of view.
Of course, this is a possible future development. We try to build the framework in order to have the highest flexibility in trying to customize it and adapt it to the different domains or requests. So, of course, and also Arctoprolog, the base technology, has been built in order to focus in on agents context. So, in order to, it has been developed to work to facilitate communication agreement between agents. And time, if we want to make this framework effective in real-life context, is of course an aspect that we should deal with or will have to deal with in the future. So, of course, we'll see it. I don't know yet. I don't know if there's someone else of the authors is there.
I see Roberta, maybe she wants to add
Yes,
some
just
comment.
to add something, but what Giuseppe said is absolutely correct. And I was really interested in the work by Stefano presented before, and so I think we have to study better timed argumentation framework. That is a thing that we haven't done already. But I can say that we start to add the concept of time in the two-prolog system, that is the base of the arg2prolog system. So I think that, of course, it is an interesting further direction. Thank you for the comments, Viviana.
Thanks to both. Any question from the audience in Parma or here online? Okay, I have another one. It should be short, hopefully. At some point, I missed some slides, as you could understand. I missed if there is any kind of approach similar to the previous one where agents could be in charge for one argument. So could you distribute arguments among agents? Does it make sense in your kind of framework? Given that it was said in the previous presentation, Laura made a comment on that. I was curious about this issue.
At the moment, we are working in another line of research. We are trying to study we are starting to study how can the distribution on agents of different arguments could be. So what are the implications of distributing the argumentation process between arguments? We released or presented our work VOA last week on these themes. So yes, of course, but the work is still at the beginning because we are trying to go slow, trying to find analyze all the aspects. But we think that it could be a fruitful line of research, so in which the arguments are shared across all the agents, and they can argue on that.
Yes,
also
actually,
preferences, because in this case, the ability to deal with the dynamic preferences in a scenario where there are many agents having different knowledge base or having different knowledge, this could be an important feature, of course.
Thanks. I do agree that this idea of distributing arguments among agents or maybe distributing agents, each managing subsets of arguments is very exciting. So thank you. I would thank the speaker.
Thanks.
Thank you. And the next paper is by Alessandro Burigana, Diego Calvanese, Paolo Felli, and Marco Montali. It's about a possibility-based epistemic planning framework. And this time I do not know who is going to present. Alessandro. Okay. Thank you.
Okay. Can you hear me well?
Now I can hear you.
Okay. So hi, I'm Alessandro Burigana. Today I'll be presenting this epistemic planning framework based on possibilities. So the idea is the following: we're going to talk about multi-agent epistemic planning as a problem, and then we're going to see how it is traditionally defined based on Kripke models. So the formalism based on Kripke models. Then we will move to possibilities, which is the underlying formalism that we use to describe states, epistemic states, and also actions. And then we're going to see Delphic, which is the comprehensive formalism based on possibilities. So multi-agent epistemic planning is an extension of classical PDDL planning, where we want to have agents that can reason about the perception of the world, that is the physical world, so the fluence, and also they have to reason about the perspective of other agents, so the knowledge and or the beliefs of other agents. So when we deal with epistemic planning problems, domains actually, the plans may refer to two main kind of information. So both physical information, so we want to say, okay, the world has to be in a certain way, but also we want to say how the knowledge and or the beliefs of the agents should be at the end of the plan. So we have two main components. The first one is epistemic states, and as I mentioned before, we have two kinds of information. We have the information described by propositional atoms, which is called factual information, and then we have epistemic information or doxastic information. In our case, since we want to deal with beliefs of agents. So as a first example, which is an example that we carry through the whole presentation, imagine we have two agents, Charlie and Lucy, in a room. Charlie places a coin inside a box without Lucy looking. So Lucy knows about the coin, but she does not know about its position. Only Charlie knows which position the coin is. So we have here two possible worlds. The one in which the coin is heads up and the other one which is tails up. And we're going to consider the perspective of Lucy. So she does not know which one is the case, but she knows that Charlie knows. Then, for example, we may let Lucy open the box and peek inside of it. So she learns about the coin position. Now, Charlie is aware of this, of the action of Lucy. Lucy is aware that Charlie is aware, and so on. So they will have this common knowledge about the action taking place. And here again, we have two possible events. Either Lucy learns that the coin is heads up or tails up. So again, two possible events. And we want to also represent the perspective of agents with respect to this event. Now, let's talk about how Kripke models can encode this kind of information. So we talk about multi-pointed Kripke models, and which are used to represent epistemic states, or E-states for short. So these are pairs, where M is a classical Kripke model, and WD is the set of designated worlds. So it's a non-empty set of worlds which represent the perspective of a particular agent. So in our case, we have two possible worlds, and both of these worlds, heads or tails, are designated, standing for the perspective of Lucy. So she does not know which of them is the true world. And similarly, we have event models. Event models are used to represent actions, and we have four main components. So we have a set of possible events, which we call domain. We have accessibility relations, similarly to Kripke models, and this component assigns, with this component, we deal with the beliefs, the perspective of the agents about which event is taking place. And to each event, we give a precondition and a postcondition. So for each propositional letter, we say which condition has to be satisfied in order for this change to happen. And again, we have a pair, multi-pointed event model is a pair where ED is an empty set of designated events. And here again, we say we consider a perspective of a particular agent. So then we have the notion of product update. And this is how we apply the effects of an action given a particular state. So we have to calculate all the different components. So we have to come up with a new state. We start with the set of possible worlds. We do the cross product. So the new possible worlds are going to be pairs world event, such that the precondition of the event is satisfied in the previous world. Then we deal with the beliefs of agents. So given an agent I, we say that the worlds WE and VF are in the accessibility relation of I if the perspectives previously held by I in the state and in the action match somehow. So if basically, if I'm in world W and I apply the event E, and same goes in D and F. So if in W, agent I perceives V as possible, and in E, I perceives F as possible, then it would make sense for I, given this world WE, to perceive as possible VF. Then we deal with the interpretation of the atoms. So an atom P is true in the world WE if the postcondition for P is in E is true in W. And finally, the designated worlds are the pairs WE such that both W and E were designated in the previous state of affairs. So now we can see our example in a graphical representation. So this is the initial state. As you can see, we have two designated worlds. Designated is indicated by this double circle. W1 means heads up, W2 means tails up. And this is the perspective of Lucy. So she has uncertainty. So this double arrow here means that Lucy considers possible both W1 and W2. But also she knows that Charlie knows. So we can see that we have these self-loops with Charlie, but Charlie does not believe the other world to be possible. And this means that he knows about the coin position. Then if we take this action, this is the action in which Lucy picks inside the box. So you can see that she does not have any uncertainty. Either she learns heads or she learns tails. So this bracket notation means that event E1 has precondition H. So to learn heads, it must be that the coin is actually heads up. And ID means that we do not have any change of the atoms. So we have the identity function to represent the postcondition. And this is the state, the resulting state. So we have two events, the pair W1, E1, in which heads is learned, and the pair W2, E2, in which tails is learned. And until we actually perform the action concretely, we have to account for both of these possibilities. Since at planning time, we do not know actually the state, the actual state of affairs. So we have to consider both of these. And then when we actually perform the plan, the state would collapse in one of the two worlds. Now let's move to possibilities. Possibilities are going to be used as formalism to represent both states and actions. And these are objects introduced by Gerbrandi and Groenewald in 1997 based on non-well-founded set theory. But first of all, let's see why we use possibilities. First of all, we implemented already a slightly different formalism for possibilities, framework based on possibilities in a planner called EFP. And we saw that it led to a faster implementation due to the fact that possibilities give a more compact representation with respect to cryptic models of epistemic information. Secondly, and we are going to see this in the next slide, possibilities provide a more fitting intuition to describe the perspective of an agent. And finally, as these objects have a tight bond to Kripke models, we can exploit the results which we already have for Kripke models also to possibility. So formally a possibility U, and we're going to use this color to represent possibilities, is a function that has two components. The first component assigns to each atom P a truth value, 0, 1, and this component plays the role of the evaluation function of Kripke models. The second component associates to each agent I a set of possibilities, UI. So this set of possibilities, which we're going to call also information state, plays the role of the accessibility relations and represent all the possibilities that agent I considers to be possible, to be true or admissible in world U. So each possibility intuitively represents one possible world, but inside of it, we have all the information that we require. So this is in some sense, this is a box, is a sort of wrapper in which we put all the information. So it's almost as if you represent one perspective, one particular perspective. And this is why previously I said that this gives a more fitting intuition for describing a perspective. Because we do not have different components as in Kripke models, worlds in one side, accessibility relations, and then the evaluation function. We have all the information within one single object. And then we have possibility spectrums, which are non-empty sets of possibilities, of designated possibilities. So this is how we represent a epistemic state with possibilities. As I mentioned, we have a tight bond between possibilities and Kripke models. So if we have a Kripke model M, as we can see in the left side here, we can obtain a possibility through this function, this declaration delta. And delta is a function that assigns to each world of the Kripke model one possibility, respecting both the interpretations of the fluent and the accessibility relations. And the idea is the following. To each one of these, to each world W, we give a possibility W in red, such that WP is 1 if and only if the world W is interpreted in the set of the worlds in which P is true. And then recursively, we determine the information state of agent I by calculating this set, which is a set of delta W prime, such that W prime is a pair in the accessibility relations R1. And an important property of this declaration is the fact that to each world, to each dissimilar world, we give the same possibility here. So in this sense, for this reason, possibilities are much more compact. Also, as a notation, we call the Kripke model the picture and the possibility the solution. Now, let's talk about how actions are modeled. So we define a new fresh propositional atom, which we call free, which is used to describe the precondition of an event. And given this, a possibility-based event model, or for short M, is a function E that assigns to each atom E prime a formula, and similarly then to each agent a set of M's. So this is the information state. So E intuitively is a possible interpretation, a possible event of an action. This component, E pre, gives us the precondition of the event. The postconditions are represented by EP for each atom P. And then EI is the set of all the events that I considers to be possible in E. Then again, similarly, event spectrums are sets of non-empty set of designated M. So these are the designated events which represent the perspective of some agent. Now let's see an example. So here we have the our state and our action, and this is how this is the solution, as we mentioned before. So this is the possibility spectrums that is relative to this particular state. We see that W1H is 1, since H is true in W1, and similarly for W2, H is 0, sinus here is false. And then look at the information states. So in W1, Charlie believes only W1 to be possible, and similarly for W2. And Lucy has this kind of information state, which mirrors the information given here. And here we have the same representation, the same kind of example. Now, so a quick recap, we had a lot of definitions so far. One possibility represents one possible world, so atoms plus beliefs of agents, and a possibility spectrum represents an in-state, a set of designated possibilities. Similarly, a PEM is a possible event. We have preconditions and postconditions and beliefs, and an event spectrum is an action, so a set of designated PEMs. So Delphic is our framework based on possibilities, which is a short form for an acronym for Delph planning with a possibility-based homogeneous information characterization, which homogeneous means that both states and actions are represented using possibility. So now we have two components. We need a third one, which is the union update, which is the update operator, similar to the product update in Kripke models based formalism. So first we define the union update given a possibility and an event, which we call U prime. So this is the update. If the precondition is not satisfied, then we set U prime as the empty set. Otherwise, we say that P is true in U prime if and only if the postcondition for P in E is true in U. And then we recursively calculate the information state for agent I as the set of updates VU times F, such that in U, agent I considers V to be possible. In E, agent I considers F to be possible. And then the event F is applicable in V, meaning that the precondition is true in V. Now, given a possibility spectrum and an event spectrum, so the whole state and the whole action, we define the product of the union update of these two elements as the cross product between the designated possibilities with the designated events, such that the precondition of the given event is true in the possibility. Here. So this is a very similar definition, with respect to the product update, and we're going to see that they are related somehow. So let's continue with our example. We have this, our state and our action, and their two solutions, which we saw before. So if we apply the definition, and we call WXY the product, or WX with EY, we have that capital W, U times capital E is the following effect, which is basically applying this definition on the bottom of the page. So now we notice immediately that E2 cannot be applied in W1 because we cannot learn tails if the coin is heads up. And similarly, we cannot learn heads if the coin is tails up. So these two are the empty set and are not considered. So our final state would only contain W11 and W22. So since here we have no postconditions, the fluents, the atoms, are going to be unchanged. And now let's look at the information state. So what Charlie is going to believe in world W11. So if Lucy learns head, he is going to still believe that head is true. He will not change his perspective, and he will not actually learn nothing new. Lucy, on the other hand, will restrict her perspective. So now she believes that both of these worlds are possible. And after the action, she will only believe that heads is the case. And similarly, for the perspective in W2 too. So graphically, we will have that this possibility spectrum is the solution of the epistemic state that we calculated before using the Kripke model-based formalism. And this is not a case. In fact, we proved that these two formalisms are actually equivalent. So this means that if we had an action, applicable action in an state, and we have their solution. So E is the possibility, is the event spectrum, which is the solution of the action, and W is the possibility spectrum, which is the solution of the E state. Then W prime, the updated version, the updated state, is the solution of M prime WD prime, which is the product update of the two previous states with a free key representation. So this means actually that our new formalism is equivalent to the previous one. Okay. To conclude, we have provided a formalism for epistemic planning, which is entirely based on possibilities. So both states and actions are based on possibilities. And we were driven to this new formalism based on the experimental result we had in previous implementations of the planner EFP. So we have a more compact representation, a more faster implementation, and also we have this semantical equivalence with this script key-based formalism. And right now, we're actually implementing Delphic within the planner EFP, and we want to users to be able to give their own actions. So we have a high-level customization, and so in this way, we're going to be able to encode a wide variety of real-world scenarios, and we'll have this very comprehensive tool so people can play with. Okay, so this is it for the presentation, and thank you for the attention.
Thank you. Are there any questions from the audience in Parma? I see one question by Roberta. Maybe, Roberta, you can turn the microphone on and make your question.
Yes, thank you, and thank you for the presentation. It's more a curiosity. I was wondering if dynamic epistemic logic is exploited in some real-world application, and if yes, which ones? And also with respect to your extension that is based on possibility, which are the main advantages in this real application? Are just in a more compact representation and in performance, or you can envision something more?
Okay, so at the moment, the dynamic epistemic logic frameworks are more theoretical. I'm not aware of any practical use. I recall that Thomas Bolander is using some, doing some experiments in which they have this little robot that interacts with human agents, and the robot and the humans have to cooperate to get a plan. So we have this DEL-based formalism implemented inside this robot, but it's more like restricted to research purposes. I'm not aware of any DEL-based planning framework used as a more general audience kind of thing.
Okay, thank you. But it is really interesting also the interaction with robot and so on. Thank you so much.
Thank you.
Thank you. And I see Laura.
Hi.
Easy. Hi.
I would like to ask, I remember last year there was a work by maybe Pontelli and Dovier dealing with multiple agents, multi-agent epistemic action logics. And if I remember well, this work was as well based on possibility and on an encoding of these possibilities based on set theory, or on a set theoretical approach in ASP. And I don't believe, maybe they don't, they did not deal with planning directly. I don't remember. Maybe there might be relations with that work. I don't know if you are aware of that work.
Yeah, the work is also by me me and Francesco Fabiano.
Ah, sorry.
Yeah, I'm
so
going
which
to
is the relation?
Yeah, there is a strong relation actually. And the work, I am going to represent the work tomorrow actually. And basically the work was done last year. So there is a difference in which in that work we consider only 3 kinds of action. So some presets form of actions, on-tick actions, sensing and announcement actions. And this framework is much more general as everybody can just create their own action and put it inside the planner. And the work you're talking about was simply a planner based on ASP, which encodes basically, it was encoding the possibility-based framework just as EFP here, but not with Delphic. The Delphic is a new item which we've been developing in the past few months. So now we have a more general framework actually, which as a plan I do not mention, but thank you for remembering me. We're going also to implement Delphic inside of this ASP-based encoding.
Thank you very much for your answer.
Thank you. Other questions? Okay, if not, I would thank the speaker again. Thank you. And I suppose we are on time, and people there in Parma is waiting for their coffee. So I don't know.